This lesson is on applications of common logarithms. So, as you can probably imagine, now that you're able to solve exponential functions where we have an unknown in the base, that now makes it possible for us to go back into applications of exponential functions and solve for a wider range of questions that previously we would have had to graph in order to solve, which is a bit of a hassle. So let's start right off with a few examples. So how long to the nearest day will it take 500 bacteria to grow to 1200 bacteria if they're doubling every 4 days? So you probably recall from exponential function questions we looked at earlier that this is an exponential growth type problem. And the formula, n at t is equal to n naught times 2 to the t over d. And t, of course, referring to the total time, d referring to the doubling period, and then n naught being the initial amount. And previously when you solved these questions, unless they were cooked up in a way that you could get a common base, we would either be looking for n at t or possibly n naught. So we plug in all the information to this one. We know we're starting with 500 and it's ending up with 1200, and the doubling period is 4 days. So it's going to look like this. 1200 is equal to 500 times 2 to the t over 4, unknown in the exponent, the total time. How long did it take? The method is always the same. You try to express one power equal to another, so it means you're going to have to divide out the 500 from both sides. It's not absolutely necessary, but it really makes the math easier. And in doing that, we'll get 2.4 is equal to 2 to the t over 4. You should take a quick look to see if a common base can be found, because if it can, then you can bypass the logarithms. Of course, you cannot in this case. So we do take the log of both sides. So the log of 2.4 is equal to the log of 2 to the t over 4. And we apply the power property as always. That's how we get the exponent by itself, and that's going to bring that t over 4 to the front. Now there's a few choices you have at this point, but I really recommend getting rid of the denominator that is offending you. So we multiply by 4, and if you multiply each of the terms by 4, you will then get 4 log 2.4 is equal to t log 2. So the denominator is gone, and now we just have to isolate t by dividing by log 2. And that will give you 4 log 2.4 divided by log 2. And you just push that right through your calculator. Remember to close brackets, but it's just 4 log 2.4 divided by log 2. Basically just the way it is. And if you do that, you will get t is equal to 5.05. And because we're asked to take this one to the nearest tenth, we can now state that it will take 5.1 days to grow to 1200 bacteria. Let's take a look at another one. A sample of radon-211 took 29 hours to decay to 30% of its original mass. So what is the half-life of radon-211? And this one is going to the nearest tenth of an hour. Well, the formula we work with is very similar, but instead of having a base of 2, we have a base of 1/2. This is exponential decay, and we note that h is the half-life. So that is the time it takes for it to decay by half. So we would then get 30 is equal to 100 times 1/2 to the 29 over h. So a couple things. Be aware that if you're dealing with percents, we did see this earlier, start off with the initial amount being 100 and then the future amount being 30. Safest way. And also be careful with this case because we have the unknown on the denominator in the exponent. It might complicate things a little bit, but stick with the game plan. So as we go through this one, same situation we were in last time, we need to express this as a single power. So we divide everything, or one power equal to another power. We divide both sides by 100, and that will give us 0.3 is equal to, and I'm going to decimalize the 1/2 as well, so 0.5 to the 29 over h. Because I'm going to be using my calculator for it, and because that's such an easy decimal to work with, it will help us. We cannot get a common base, so we do take the logarithm of both sides. So that we get the log of 0.3 is equal to, I'm going to cheat here a little bit too by going 29 over h log 0.5. So I'm going to take the log of it and apply the power property at the same time. Now don't be worried because the fraction has the variable on the bottom. Do exactly what we were doing before. Multiply both sides by the denominator to cancel it out. And all that happens is we will get h log 0.3 is equal to 29 log 0.5. So no big deal. The h is just moved over to the other side. And when you divide now by log 0.3, we get h is equal to 29 log 0.5. Now you don't have to write these brackets in, of course, but you do need to put them on when you're running it through your calculator. And then log 0.3, although you don't need the zeros when you're keying it in. Now you can go 29 times, or you can just go 29. Your calculator knows to multiply it, so it's not really necessary. So 29 log 0.5 divided by the log of 0.3, and you will get h is equal to 16.69, and then I think 57. 8. You don't even need to write all these down. When we take it to the nearest tenth, then we would round it to 16.7 hours. So the half-life is 16.7 hours. Take a look at another one. Strontium-90 has a half-life of 25 years. How long will it take a sample of this element to lose 3/5 of its radioactive mass to the nearest tenth of a year? Now these questions, even the last one, aren't really that difficult. It's, the details are what's caused problems. And this is a good example. You see, the formula, any of these growth or decay formulas deal with the amount remaining, not the amount that's lost. So when you see a question like this, although it is going to be the decay formula, the half-life formula, you got to remember that if 3/5 is lost, then 2/5 remains. So that would mean that when we put this into our formula, we have to end up with a future amount of 2/5. We're starting with 1. So the original amount is just 1. Now I know that some people will turn all this into a percent, and that's also okay. You could start with 100% and then end up with 2/5 of 100, which is 40%. But this is a nice, neat way to do it. And again, I would recommend decimalizing everything because that's how we're going to solve it. And keep in mind that we are looking for the total time. So if we did take this as a decimal, 2 over 5 is equal to 0.4, and that would be equal to 0.5 to the exponent of t over 25. And here we are again. You take the log of both sides. So the log of 0.4 is equal to t over 25 log 0.5. So the power law gets applied at the same time. Multiply everything by 25 so that you can cancel out that unwanted denominator, and you get 25 log 0.4 is equal to t log 0.5. And then t, when you isolate through division, will give you 25 log 0.4 divided by log 0.5. And then you just run it right through. So 25 log 0.4 divided by the log of 0.5, and you will then get t is equal to 33.048. So it will take to the nearest tenth 33.0 years. So that's how those questions go. They're all basically the same, but you have to make sure you set them up properly and be very careful with the algebra. Now the next one, it requires the compound interest formula, but I brought this example in just to remind us of a few things. Now the question looks innocent enough. This guy invests $256 into an account, and it's compounded annually for 8 years. And then at that point, it's worth $299.94. And we've got to figure out what the annual interest rate is to the nearest tenth of a percent. So this is our formula. A is equal to P times 1 plus I to the n. Remember, the compound interest formula is designed for questions like this, but it's also useful for questions that are like population growth. Any sort of small-scale growth is appropriate for compound interest. So our future amount is $299.94 is equal to 256, the original, times 1 plus I to the exponent of 8. And what makes this question interesting is that a lot of people make mistakes with it because they get into this groove where they take the log of everything. This is not a type 2 exponential equation. The unknown is not in the exponent. So when you're solving this, do not take the log. Very important. The unknown is not in the exponent. Now you can actually use logarithms to solve this, but it's inserting a few extra steps which aren't helping. So let's solve this the conventional way. 299.94 divided by 256 will give you a decimal, 1.17164. I'll keep it on my calculator. It might come in handy later on. And this is a type 1 exponential equation, which means that we want to get at the base, this I, and the only way we can do so is to get rid of that exponent. So we raise both sides to the 1 over 8. So 1 plus I is equal to that number on your calculator, raise it to the exponent of open bracket 1 divided by 8. And that way there's been no rounding at all. So raise to the exponent, open bracket 1 divided by 8, and you will then get 1 plus I, at least according to my calculations, equal to 1.019998 when I round. We're solving for I, so it makes sense to subtract the 1 away, giving you 0.019998. And the only other thing that we should be aware of is that we do want this one to be as a percent to the nearest tenth. So we multiply by 100 to turn it into a percent, and that becomes 1.9998%, which if we take to the nearest tenth, the annual interest rate is 2.0%. So do not just assume that every question is going to require logarithms. It's only when the unknown is in the exponent and when you cannot get a common base. I'm going to change gears a bit and look at a couple other, or one other type of application, Richter scale problems. They don't fit perfectly into the growth decay setup, but they are applications of common logarithms that you frequently see. Now, the Richter scale is a logarithmic scale, and it was used to measure seismographic activity, usually like things like earthquakes. So most of you have probably heard like a Richter scale measurement for this. And the nature of logarithmic scales is that they're used for exponential functions which tend to increase or decrease very rapidly. So because a logarithm is really just dealing with the exponent. When you take the log of a number, you're finding the exponent that particular base must be raised to be equal to that number. So what it means then is that you're getting smaller values. So Richter scale measurements, you're familiar with Richter scale numbers of 5, of 6. They seem very easy to use numbers, but those numbers refer to the exponent. So if you took a look at a very rough Richter scale diagram that I have here, the Richter number, which you're familiar with, is simply the number on top. But that number actually represents the exponent. And it means then that if you had a Richter number of 3, means the intensity is actually 10 to the 3 units. Now I'm not sure forget what the units are. There's some seismographic unit. But that's really what's happening. So it's a fairly intense quake, but we just count it as a 3. The other characteristic of then, when you're comparing quakes, which is what most of you will be doing, when you go up one Richter measurement, you're actually going up a power of 10. So the difference between a Richter scale measurement of 5 and a Richter scale measurement of 4 is actually 10. So it's 10 times as intense. So the Richter scale is going up much more rapidly than the numbers would indicate. So here's a pretty standard question. How many times more intense is a quake of Richter number 7.5 than one of Richter number 6.2? And the formula we pretty much always work with is this. The intensity of quake A divided by the intensity of B is equal to 10 to the A divided by 10 to the B. And it's also important to remember that this is the ratio of intensity of quake A to quake B. So IA to IB, and this is really what we're looking for. So we plug in the Richter numbers. So the A is 7.5 and the B is 6.2, remembering that those Richter numbers refer to exponents. And then we just simplify, because then this becomes IA over IB is equal to 10. 7.5 minus 6.2 is 1.3. So we get IA to IB is equal to 10 to the 1.3. And all you have to do now is put that through your calculator, and the ratio of A to B is 19.95. And that's the variable IA, IB is treated as a single variable. So the 7.5 quake is 20 times as intense as the 6.2 quake. Quake A has a Richter number of 7.9 and is 120 times as intense as quake B. Find the Richter measurement for quake B to the nearest tenth. This is the same type of question, but a little more complicated. So we'd use the same setup. IA to IB is equal to 10 to the A to 10 to the B. Just remembering that the Richter number refers to the exponent. And when we plug everything in, we get this. And we need to remember that the IA to IB, this 120, does refer to the ratio of intensity. It's 120 times as intense. And that's usually where people go wrong with these. So we replace IA over IB directly and completely with 120. And now it's not so bad, because when we try to solve it, I'll bring a new screen up for this, 120 is equal to 10 to the 7.9 over 10 to the B. We simplify the right side by subtracting the exponent. So 120 is equal to 10 to the 7.9 minus B. Take the log of both sides. Unless you're lucky enough to be able to get a common base, you go log 120 is equal to, and I'll apply the power law at the same time, so 7.9 minus B log 10. Now you're probably thinking out there, should I distribute that log 10 into both terms? Well, you can, and it's fine, and we've done those ones before, back with the early common logarithm questions. But I would actually advise you to remember that log of 10 is equal to 1, right? 10 to the 1 is 10. So, in fact, this thing is just going to simplify to 7.9 minus b times 1, which means the 1 goes away. And that gives you a much easier equation to work your way through. And all you have to do now is isolate the b. Myself, I would recommend that you take the b to the left side to make it positive, and then keep the 7.9 where it is, and then subtract the log 120. You don't have to do that, of course, but it means that you don't deal with a negative. And then b is equal to 5.8 when you just put that through your calculator. So Quake B measures 5.8 on the Richter scale. Pretty normal type of question. So that's it for applications. That really closes off the unit as well. There is going to be a section on a calculator operation, exponential regression, which is kind of a tweener type topic, and it's strictly calculator based. But in terms of the concepts and the material, that would be it, or this would be it. So thank you for